It's taking too much time to start. 5 minutes.
And the angle in this projection for projection alignment to the coordinates of properties and rules.
I'm pretty generous on homework, so not you'll see. All right, finally we are ready to start. So last time we did end the class with two types of convex function. One was strongly convex, other was quasi-convex. So any questions on this? What strongly means, what quasi means? So quasi essentially meant that look at any alpha sublevel set. What is this set? X such that f of x is less than alpha is convex for all alpha. Such a function is called quasi-convex. And what is strongly convex?
It is convex with the additional condition that it's the norm half times.
Can you just tell me?
Half mu times
F of y
is greater than equal to x plus the gradient times.
So this is true for convex functions.
Plus half mu y minus x norm.
This is called a new strongly convex function. And what property did we show? That's if and only if we showed something. Slightly loudly.
Gx is equal to f of x and gx equal to f of x. We know of x square is
Want to say this? Okay. What is this function? If this function is convex, then function f is strongly convex. This is actually an interesting quantity. It might come helpful to solve many other interesting things. So always, if you're throwing your hands around, there is one function to keep in mind. Many a times this works. Doing some trickery with, if you're manipulating functions and trying to show something, this is one interesting function. Okay, so now this convexity of this implies what? So suppose I wanted to check a function is strongly convex or not. Can you give an example for which it's easy to check whether it's strongly convex or not? This is one condition, slightly complicated derivatives, etc. Here there is no derivatives. And this is true only this if and only if derivative exists. But this doesn't involve any derivatives. So is there a function for which you can check quickly? Yeah, so that simple example is one strongly convex. Any other function? e power x. Okay, good choice. Let's see if it works. So f of x is e power x. Which definition you want to check to prove it is strongly convex? And you should also tell me the strong convexity parameter. One strongly convex, half strongly convex.
So if I just
There is a
second equation.
mu there, right? So it's very important to tell me for what mu it is strongly convex. Any mu. Wow, that would be interesting. So claim f is mu strongly convex for, that's the claim. Okay, prove it. Okay, at least give me for one mu it is true. Then we will worry about all mu's. So what about mu equal to 1? What kind of function is e power x minus x square? Yeah, half x square. Yeah. So what is g of x e power x minus 1/2 x square? The premise he is asking for that e power x is growing much faster than x square, no matter what the constant is. So is this true? Is it convex? You know 10,000 different ways to check convexity of g of x. Just tell me one. Yeah. Completely legit. What is the second derivative? Is it greater than or equal to 0?
Yeah, for x greater than 0, it will be e power x minus.
Don't worry about. So suppose for x greater than or equal to 0. What is the second derivative?
E power x minus 2 minus x. E power x minus 1.
1. Okay. So this is if I there was a mu here, what would go wrong?
X minus
No. So supposing I keep the same. So this claim is not true. Right? It has to be with respect to a particular domain that depends on mu. You can freeze a mu and then try to say something. One is so similar to my x square. There is no better. There is still just one strongly convex or x greater than or equal to 0. If I were to shift right and define a mu domain, then I would be okay. Doubt. Something's missing, sir.
So I was looking for a function,
Yeah.
which is suppose, for example, not one strongly convex, but any point, any mu if you give less than 1, it will be strongly convex.
What does it mean?
Like for any sequence mu n tending to 1 from below,
Okay.
it will be strongly convex, but not at 1.
Methodological things you can keep trying outside of the class. Any other function? So we got x squared, we got e power x. What other functions come to mind? We're doing something to actually construct without telling me. We're looking at functions which are growing faster than x square. So can there be a function which grows slower than x square and still be one strongly convex? Stop from that from happening. Is the objective clear? You want to construct a one strongly convex function which grows slower than x square. Is it possible or not? You have straightforward characterization setting that f of x minus half x square better be convex. It's an if and only if condition. We just look at a slowly growing function, x power 2 minus alpha, for some alpha greater than 0. What happens? Is it possible that that function is convex? So let f of x be some x power 2 minus alpha. I'm being sloppy here because x is one dimension and alpha greater than 0, less than 2. What is g of x? Is x to the power 2 minus alpha minus half x square. What is the second derivative of this? We have simple test. We don't have to do anything because all we're checking is the convexity of this function for which you have characterization. So what is the second derivative of this? This is simply 1, 2 minus alpha, x to the 2 minus alpha minus 1, and one more time, 2 minus alpha, 2 minus alpha minus 1, x to the power minus alpha minus. So let's erase this part. Yeah. So what can we say? This is positive. This is not necessarily positive. This is 1 minus alpha. So this is a positive quantity. This is 1 minus alpha to the power x to the minus alpha minus 1. So this is still positive for x greater than 0. This is the quantity which will try giving you trouble first. That's the first place where you will get trouble. And then there is a minus 1 sitting here. So what is the final conclusion? Is it possible?
Maybe negative.
Which one?
G double prime of x can be said.
Is it universally true?
No, it can be double.
Okay, so is there any?
G double prime of x converges to minus.
Okay, so is there any convex set over which this is strongly convex? If not over all x greater than 0? This is a clearly positive quantity. This is 1 minus alpha. This is x to the minus alpha. That's also positive. So these two are playing the roles of each other. So if x is greater than 1, what happens? Let's try to divide it into two parts. X greater than 1 and x between 0 and 1. What happens? This is something smaller than 1. This is what? Let's take alpha between 0 and 1 for the moment. X greater than 1. What happens to this quantity? This is positive. This is smaller than positive, but smaller than 1. This is also smaller than 1. So the product is smaller than 1. But what happens to this? Sorry?
Minus alpha is.
It's more than 1, possibly. But just think about it. For large enough x, that will get cancelled out. So I don't want to be precise, but for some large enough x, it won't be too large because this is at most 2. So as x goes beyond this power. So for not large enough x, this is not going to be convex. Now what happens to x less than 1? So is there a convex set over which G double prime essentially is convex or not? So in general, it will not work. That is clear. So any such function which is growing slower than x square will never be strongly convex, one strongly convex. Always remember that. Okay, any other function which is strongly convex?
So can you argue in the way that you have two functions,
Hmm.
fx and x square, half x square.
Yeah.
So the second derivative of half x square lying between the region x equal y equals to x and y equals to minus x.
Okay.
The second derivative. But
Second derivative is simply -1.
no, yeah, means one in the sense it is lying below the y equals to x line.
Yeah.
And for in the other function f, which is slowly growing,
Yes.
so it will be definitely lying below a line that was tan theta will be less than 45. So
Okay. But you see that there are points at which this is positive. So it's not universally negative. So there could be a region here for which this is true.
where the growing,
Yeah, so it just balances it out. That's all. But in general, it cannot be. So you can't say over R such a function can be strongly convex or one strongly convex. Why I'm belaboring this point is that whatever results will prove for just convex functions, they can be significantly strengthened when the functions are strongly convex. It's not a matter of few more iterations, a few less iterations. Order-wise change happens. So it's very important to consider those functions. Any other function that comes to mind other than x square e power x or x transpose qx where q is positive definite? Those are all the same essentially. In what?
sin inverse x.
Sine inverse x. Is it even convex? Forget being strongly convex.
So one reason it is between 0 to
So every strongly convex function is also convex. So at least the function should be convex. How about x power 4? Now you've essentially shown that anything growing slower than x square is not going to work. So x cube is not even convex. So what's the next best bet? It is x square, x power 4. What is x power 4? What will it look like? For what values of mu it is strongly convex? No value of mu.
Not universally.
Okay. What's the problem?
Between -1 and 1, certain elements negative.
Of x power 4 itself. No, x power 4 minus. So suppose your f of x is, what is g of x? X power 4 minus mu by 2 x square. So what is g double prime? 4 times 3 is 12 x square minus mu. Right? So what are you saying? Between x what and what? It's smaller than mu. So mu is 1.
Negatives, -1 over equal to +1 over equal.
Yeah. So you have to take care of appropriate. But for appropriate values of mu, you can always find x power 4. You can scale it up appropriately or shift it if you want. Shifting won't help. You have to scale it up. For whatever domain you want, you can just put a constant there and keep amplifying it further and further. So isn't this something wrong? So x square was strongly convex, but x power 4 is not. What is going on? So why was x power?
So between interval 0 and 1, it is growing much slower than x square and then it is faster.
So because x power 4 is faster only after 1. That's the point. And here it's exactly the opposite. So this is much more restrictive. While this is pressing an upper bound for the domain so that this function can be strongly convex. Let's give you a lower bound. Okay, so let's now go to quasi-convex function, which encompasses a large variety of functions which we proved to be non-convex. Very small.
Generalizing functions of convexity in multi-variables convexity.
Why not? Where have we chosen x to be x belonging to R? X has been Rn, right? These examples I'm doing are something else. The definitions I've never restricted myself for x to belong to R. It has always been Rn. Okay. Example which we did not discuss last time. Function which is not convex.
Not convex.
Otherwise, every convex function is quasi-convex. So what's the big deal? Tan inverse. Wow, that is interesting. So f of x is tan inverse. Why not tan itself?
The domain is convex. It goes till infinity.
Okay, so what does it look like? Can you tell me what it looks like? Something like this? Okay. So this is something like x cube in a different, like x cube was this way, this is going this. So it's like a log here and a log here. That's what it looks like.
Convergence, so doesn't go in.
Okay, so now why is it quasi-convex? Because if you put a sublevel set, let's call it alpha. So essentially it's just for every alpha, there is a minus infinity to x, which gets is sublevel set. Okay. Why is it convex? Is the shape okay with you? This is not convex. Quasi-convex is what we are looking for.
Yeah, means we are looking for all the points for which.
Not all the points. Pick any alpha.
Yes.
What is the sublevel set? All points for which the function value is less than or equal to alpha. You've forgotten, it's written here, right? So what is all the possible values for which f of x is less than alpha?
It's giving a ray, basically.
Giving you what?
A ray, one side,
Ray.
like a straight.
It's a region which needs to be convex. There's no ray here. Okay, any other function? Something we showed to be non-convex in the class, which is almost convex but not convex. This is highly non-convex. How about x times y? What did we show? What kind of function is this? Sorry? Yeah, but why is it quasi-convex? If at all? Not quasi-convex. Okay. Why is it not?
If you put any level at any alpha,
Yeah.
and you just want to see that all the points below it. So you will eventually get all the points. If alpha is positive, you will get all the points negative from 0 to here, but there will be an interval between 0 to some certain is meeting,
Mhm.
and then you will get all the.
Okay, so suppose I freeze my domain to be R plus or R2 plus, then what happens? So all your difficulties are removed. But it's not convex even after removing the difficulty. See, your trouble was a minus and a minus multiplied together will give you a plus. That was the difficulty. I remove that. Domain itself is only R2 plus. Now that can't happen. All points are X and Y, both are non-negative. Now we get quasi-convex.
Yeah.
Why?
The point is, if you will get choosing any alpha,
Mhm.
you will get a domain of the form a comma infinity, where a greater than equal to right is called.
Less than, man. Sublevel set is less than. How can it be infinity? X and alpha.
Yes.
What does the sublevel set look like? All points X comma Y such that X times Y is less than equal to alpha. How can it go to infinity?
In the one direction.
How? Multiplication, right? X times Y to be less than alpha. If you allow it to go to infinity, how can it remain below alpha? What is sublevel set?
But y is getting smaller also, right?
What is sublevel set?
Here x comma y is 1.
Yes.
But that fx y less equals to alpha.
Yes. So how can it be that Y equal to infinity is a member of this set?
Not y equals to infinity.
Then
X can be
okay, it is symmetric, right? X and Y. What is the sublevel set of this function? Right? So how can X equal to infinity sit in this?
not infinity, extending to infinity.
How?
So you can get a as small y as possible, right?
Okay. I don't know what you're doing. Okay. Why is it not?
So if we take alpha is 1,
Okay. So S1 is what?
we take 2 points,
Mhm.
1 comma,
Yes.
no, not this. We take the points 5 comma 1 by 5 and 1 by 5 comma 5.
Okay. Well, did I make it one? Yes. Okay. And
1 by 5 comma 5.
Okay.
The midpoint is continuous.
midpoint is what? Tell me that. You take half of this.
Yeah, yeah.
So half times 5 comma 1 by 5 and plus half of 1 by 5 comma 5. So what is this?
2.75 comma 2.75.
This is 1 by 10, right? So 2.6
Sorry, it's 2.61.
and this is 2.6.
Yeah, that product is with us.
Okay.
So this set is
So what happened? What's going on here? Everybody agrees to this? Right. If I were to flip the, rather than saying alpha sub-level set, make it super level set. So S bar. So this is clear, right, everybody? Now let's define S bar of alpha. to be x comma y such that x times y greater than 1. What do you think? Is S bar convex? Okay, so then what should be the classification of x times y?
Classification.
So you define x times y to be quasi-convex. If every function is quasi-convex, then the sub-level sets are convex. If I start to look at super level sets, what do you think the appropriate definition should be? What else can it really be? So is x times y quasi-concave? If not quasi-convex?
So quasi-concave means that you define quasi-concave to get a super level category.
All the analogies have been going along the same way. Everything with a negative sign, you turn from convex to concave. Similarly here, for the quasi-convex, we have sub-level sets. Now it is a super level set. So x times y ends up being a quasi-concave function, but only over R2 plus, not over R2. Okay, any other interesting function? So when we're asking for a definition or an example of a quasi-convex, it's okay to give a quasi-concave, because everything will work with a minus sign there. That much is clear, right? If I put a minus there, all the inequalities will be reversed. So if x times y is quasi-concave, a minus x times y should be quasi-convex. Again, over R2 plus. So whenever I'm looking for an example, I'm completely okay with a convex or a concave. Any other function you think which is not convex but quasi-convex? And functions can be quasi-convex and concave simultaneously. Be advised. That's an example of a function which is quasi-convex and concave.
Minus x square.
Minus x square.
Y equals to
Why is minus x square quasi-convex?
every sub level set will be convex, and it is a concave function.
It's clearly a concave function, that much is clear. Why is minus x square? What are sub-level sets of minus x square?
Say
How do you take square root of a minus? You'll be in trouble.
Equals to minus.
Minus x. That's already convex and concave. So it better be quasi-convex also. These are not the examples you're looking for, right? It's only quasi-convex and concave. Every convex function is also quasi-convex. Not interesting. It's not very difficult. What's the first function we look at as concave? Why is log not quasi-convex?
log x is less than or equal to so x should be less than or equal to e to the power of that.
Yeah.
So that would make it
Yes. So, yeah, so log is one such example. So there are examples of all these types which are non-linear. The linear is essentially the only function which is both convex and concave. I am hazarding a guess that there is no other function. What?
If I take another example.
Yeah,
If I take x to the power 2y3 plus y to the power 2y3 plus 4.
equal to 1. What kind of function is this? That's a set.
Yes, I'm taking the one boundary of S.
Define a function or a set. Don't combine the two. What you define to me is a set. X comma y such that x power 2 by 3 plus y power 2 by 3 is 1. I'm not looking for a set, right? I'm looking for a quasi-convex function that is concave. So give me a function.
X to the power 2 by 3
Okay. Why is it quasi-convex? Why is it concave? What is so special about 2 by 3?
Like any other x.
If at all I would have taken square root x. What is square root of x, by the way? Is it convex or concave? Yeah, and is it quasi-convex? It is, right? So there's hardly anything to check there. So all essentially they're all log type functions. Okay, anything else? Was x by y convex? Did you prove convexity of x divided by y for y greater than 0?
Sorry, what did you say?
X by y. One by x is convex, but was x by y convex? No, not too hard. F of x comma y, x divided by y. Is it, first of all, check, is it convex or not? It's not convex. Did you go home and not fall for my trick? All we did was we looked at the determinant of the Hessian, which was not what we wanted. But that's not what the check is. What is the Hessian, by the way, here? Can somebody tell me quickly? 0, 0. This one? -1?
-1 by y square.
Y square. What is?
Symmetric.
Okay. Fine. So, what can we say here? And y is greater than, always remember, y is greater than.
Last matrix 2x by y.
Sorry, this one?
2x by y.
2x by y
Cube.
cube. Okay. Fine. So what's the only way to check whether some, let's call it z transpose del square f of x y z is greater than or equal to 0. Okay. So let's z1, z2. So hoping I'll not make a mistake. Z2 times 1 by y square with a minus sign. Right? And what else do I get? 1 and minus z1 by y square plus z times 2x over y cube. This is my vector, which is going to get multiplied with z1, z2. So far, so good. So what is this? Minus z1, z2 times 1 by y square. And this is z2, right? Minus z1, z2 by y square and plus z2 square 2x over y cube. I've done everything right. Now, what can you say about this being greater than equal to 0? Or not being greater than equal to 0? We in fact want to prove that this is not true. The x by y is not convex. So can you produce a z1, z2 for which this is not positive? That would, if you can show negative, that's good enough. So leave, I thought you would have done this exercise at home. So leave this exercise. Now can you tell me, is it convex, quasi-convex or not?
If you x equal to y to 1 and z1 greater than z2, then we get
Negative. Oh, good. If I leave something, I expect you to go back home and just check it for yourself. It's always good to know x by y is not strong, not jointly convex. Now question is which quasi-convex? What is the alpha level subset? What is this alpha? Is x comma y such that x is less than alpha y. Okay. So take 2 points. What like the simplest thing you can do? So x1 y1 and x2 y2, which belong to S alpha. So now lambda x1 plus lambda x2 comma lambda y1.
sorry.
What's happening to this point? I know that x1 is less than equal to alpha y1 and x2 is less than equal to alpha y2. So what is this whole thing less than equal to? So lambda x1 plus 1 minus lambda x2 is less than alpha y1 plus alpha lambda 1 minus lambda y2. So this is alpha times lambda y1 plus 1 minus lambda y2. So first principles, nothing really interesting going on. It is quasi-convex. It will turn out this also quasi-concave.
It's a half-inch.
Yeah. So such things are called quasi-linear. A function which is both quasi-convex and quasi-concave is called quasi-linear. Your question. So there are lots of functions which we would like it then to be convex, but they are unfortunately not convex, but they end up being quasi-convex. And there is some theory we can develop for quasi-convex also. That's why we talk about. Okay. So now, given our definition of quasi-convex theorem, sometimes this is what I'm going to write is also used as a definition of quasi-convex. A function is called or is quasi-convex if and only if f of lambda x plus 1 plus 1 minus lambda y is less than equal to max of f of x from f of y for lambda between 0 and 1 and xy belong to the This is an interesting characterization. Sometimes this is taken as a definition, and then because of this theorem, you can go to that definition also. Any interpretation for this? In pictorial, geometric, whatever. So for convexity, we have a different definition completely. But the left-hand side is less than lambda times f of x plus 1 minus lambda times f of y. Replacing both by just the max of the two quantities. So that is allowing us extra freedom compared to the convex function. So we had this interpretation that the chord lies above the function for the convex. What is the interpretation here? The right hand side is no longer the chord.
It is above the chord.
Where is the chord? There is no chord.
Yeah, so if we have a chord joining the f of x, then the max f x, max value is even above the chord.
For a convex function, what we demand? That the value here should be larger than the value here. So this was x, and this is my theta, which is theta is nothing but lambda x plus 1 minus. So what did I demand? That f of theta was smaller than lambda f of x plus 1 minus lambda f of y. So this was f of y, and this was f of x. Now what am I demanding?
Now we are just drawing a line parallel by the
Let's
of the two. It should be below this time.
So the function should just lie below. I don't care what is going on in between. So it's losing all its nice shape properties in some sense. So supposing a function of this type is now a valid function, which wasn't the case before. So it's always remember to visualize things. How do I create a quasi-convex function? This is a quasi-convex function. What else can I do? Can I do squiggly things like that? That's okay. No? Well, what about the function of this type?
That's good.
No, not right. It's some function. Is this quasi-convex?
F of x less than or equal to alpha, that domain will have a lot of rates.
That's so they're not contiguous, they're not convex. So this is still not allowed. But this is now allowed. Okay. So now, at least, so what's the freedom really we got? We had to lie a bit below this. Now we can lie below either of like the larger of the two. That's the freedom we have given ourselves. Okay, so does anybody see the proof? Proof is kind of straightforward. There is nothing technical going on. All we have is a simple definition that all alpha level subsets are convex. That's all we give.
Quasi-Convex.
Okay,
And then let x1 comes. X comma
show this. We're going to start with our definition of quasi-convex and we'll show this that that's also true. Okay. So all we have is that for any alpha, the alpha level subset is convex. That's all we got. So all we need to do is to make a choice of alpha. What is the choice?
max of
What else there is? Sometimes your hands are little tied very tightly. This is one such example. There's nothing much to really do. What do we have? By our, what are we following? By definition, for F to be quasi-convex, S alpha is convex for all alpha, right? So let's choose one particular alpha to be max of f of x comma f of y. What will happen? Why do I get what I want? I want this to be true.
So which quasi-convex then for lambda x, like
Hmm.
lambda x plus 1 minus lambda y should lie in S alpha.
So let's say these are 2 points. This theta. So my theta is lambda x plus 1 minus lambda y.
Right.
Sorry. Now what is f of theta?
this first all.
Theta belongs to what? I need to invoke convexity of something, right?
Theta lies in X alpha.
Theta belongs to this interval x comma y by definition, and all alpha level sets are convex. So what do I get?
So theta is less than or equal to alpha.
Everybody fine? No, if not clear, ask me. This is the definition we have. That's all we really have. Since this is true for all alpha, I'm just picking one particular value of alpha. Okay. So now at that value of alpha, what is happening? Theta belongs to this. So f of theta better be less than alpha. And alpha is nothing but that value which I want to prove. So this direction is straightforward. What about the reverse direction? So suppose I'm given this, what should I do? So now we are given that this is true for all x comma y belong to the domain. You want to prove that all sublevel sets are convex.
I belong to S alpha. So then
What is this alpha?
the
For any fixed, you choosing any special alpha?
any alpha.
Any alpha. Okay.
So then f of x must be less than or equal to alpha. And f of y must be less than or equal to alpha. Because it's in the sublevel. We are defining x comma y to be in the sublevel for alpha.
No, this has to be, what you're given to you is x comma y belongs to domain of f.
So we have to prove that S alpha is convex, right? For any alpha.
Yes.
So let x comma y belong to alpha, S alpha.
Okay.
And so f of x must be less than or equal to alpha.
Mhm.
And f of y must be less than or equal to alpha. So that implies that the maximum of both of them must also be less than or equal to alpha.
Yes.
So then f of lambda x plus 1 minus lambda y
I need to prove the convexity of it, right?
Yes.
Ah, okay, that's what you're doing. Fine. So you're going to prove that f of lambda x plus 1 minus lambda y also is less than alpha.
Max, but we also saw that max is less than alpha.
Yeah, that's the proof. That's really the proof. I'm not all right. That's just one liner. If you could start with alpha equal to max of this also. You don't even have to say alpha. You could just again the same thing. Pick alpha equal to max of the two, and then define that sublevel set. And for every alpha below and every alpha above, also you'll define. So how would you take care of the case where alpha is smaller than the two quantities? So what you're just tell me what you're trying to do.
Yeah, so alpha is some just some real number.
Okay.
So now let's add. So S alpha is all the x such that f of x is less than or equal to alpha.
Yes.
So then let x comma y belong to S alpha.
Let x comma y belong to S alpha.
So then because if we find S alpha, like the f of x must be less than or equal.
Yes. So now I'm interested in this quantity lambda x plus 1 minus lambda y. All I want to show is that it should be belonging to this. Now what is lambda x plus, so what is the property x satisfies? F of x is less than alpha. Second property is f of y also is. Now what?
So if both of them are less than alpha, then the maximum must also be less than alpha.
Okay, so max of f of x comma f of y is also less than equal to alpha.
But so
Okay.
f of lambda x plus 1 minus lambda y is less than or equal to max.
F of this by definition, you can call it theta, is less than the max of this comma this. Therefore, theta belongs to
S alpha.
all right. So there are so this was our correct like similarity with respect to convex functions. Convex function, we have something stronger. Compared to that, we've relaxed it to max of this. Now we also derived some if and only if conditions for convex functions, right? So suppose your quasi-convex function is differentiable. Okay. So what was in the convex domain? If and only if condition for a function to be convex, f of y was equal to f of x plus derivative of fx minus y minus. In the quasi-convex world, what you end up getting is if and only if for x, y belong to the domain of f of y less than equal to f of x, then the gradient of f of x times y minus x. So this condition is same as quasi-convexity. Can somebody interpret it? You don't have that. That's stricter. So as soon as f of y is less than f of x, if this condition is implied, then that function is quasi-convex. And if it's quasi-convex for any such point, this is also true. Okay. Even if you can give an interpretation, can you compare the two and say something is implied in one case which is not true in the other?
But it's quasi-convex, then it makes it convex, then this thing will go in. Because from that.
No, we already know that a convex function is quasi-convex. It's only no. What I meant was something which holds in the convex case, some assertion which will not in the quasi-convex case. We by comparing these two inequalities. So what if the derivative of f of x is 0? What happens in the convex case?
Pi is greater than or equal to.
What's the implication of that?
So it has a minimum.
At least local minimum. Can you say anything like that here? If the gradient at a point is 0, is it a local minimizer?
The reverse implication is not you can't change.
So we construct an example for a quasi-convex function where the gradient is 0, but it's not a local minimizer.
So like x cube, let's say, we can take 0.
Yeah.
So over there, the derivative is 0.
So something very nice, we've been doing this since 7th standard or something. Taking the derivative and putting equal to 0 to find the minima. Doesn't hold if the function is even quasi-convex, forget not convex. So this condition I will let you prove. It's very similar to what we did here. So this won't be part of homework, but whatever I leave as exercise, the advice, I assume that you're going to go home and do it. So I'm not going to come and check for you. So similarly, you can also get your second derivative conditions. I'll just state them. So for quasi-convex, you get similarly y transpose del fx equal to 0 implies y square the Hessian. So this proof you can find in the book. And there is also a negative, like a reverse implication. So this is true for y not equal to 0, for all y not equal to 0, then the function is also strongly quasi-convex. So quasi-convex function, if this is true, then this is also true. If this is always true for y not equal to 0, then the function is quasi-convex. So both of them you can find it in the book. Sorry? Y transpose, not square. Thank you. Any questions? Sorry?
Derive some property from that.
Which one?
This one.
From here to here?
No, as in this thing holds for convex functions as well, right? This, because it's quasi-convex, it holds for convex functions as well.
Yeah.
So then, like for the second question, the first assignment, we can use that to prove that at every step the distance keeps getting smaller and smaller. Like, so
If you can derive it, yes.
I just like directly wrote that, I didn't prove it.
I've never said that that's not good enough, right? Let me have a look at it. In general, unsubstantiated statements are not say the best way to go forward, because suppose that happens to be false, everything else falls apart. But if it's a universal fact, you can see it, it's easy to visualize or something, it's okay. Okay. So before we go on to really doing optimization, there is something interesting. It's called, you might have seen it also before. called by different names. So let's call it the conjugate function called convex conjugate, called Fenchel conjugate. Conjugate. Okay. So those two, I'm not necessarily specializing it for f to be convex. For any function f Rn to R, I'm going to define a function f star. So going from Rn to R, which is given by f star of y. It's an interesting function. Y transpose x minus f of x and supremized over x belonging to, just stare at it for a while. That's the function definition. So what is it telling you? Suppose my function is some weird, let's say this is my f of x and this is my x-axis. What will f, so fix a y, everything one dimension. Fix a y. Can you tell me what is f star of y for this function? And let's say what does the line x times y look like? For a fixed y, it will be some slopey line. So this is my line, x times y for a fixed y. What is it demanding? Supremum over y transpose x minus f of x. So can somebody now see what is going to happen for this particular function?
Become function line between.
Sorry. Wherever the gap between this line and the function is the largest. Can somebody tell me visually?
There. It keeps getting larger. I mean, where does it, the function keeps increasing, then it will keep getting larger.
Okay.
So,
But look at the soup, that becomes negative. There's no mod there.
oh yeah, depends on.
If there was a mod, then what you're saying is right. There's no mod. So in fact, it's happening here. It's something like this distance. So you can call it, let's call it here, a translation of this line, which goes and touches that. Literally, that's what is happening. So just translate. It picks up even cloth. And this length is actually f star of y. Is it clear what is going on? All I've done is I've just shifted it down. If you don't like this shifted down line, don't worry about it. This line is okay. All I'm looking at is the difference of this minus the function and looking at the point which has the largest such difference. What will happen here? Why not here? So So this is the only place where xy is actually above f of x and the largest way. It's okay. The names don't matter. There are many. I started with saying it's known by many names. We'll call it the conjugate function. All right. So this is what, in terms of visualization, this is precisely what this function looks like. So this is
For a particular choice of point.
yes. As you keep changing y, you'll keep getting a different value. So now suppose somebody gave me this. Why is it interesting? I'm doing optimization, right? Why do you think it's useful to know something like this?
So if you take optimization, you can take a dual of it.
Have I used the word dual? No. I don't even know at this point what a dual is. So I'm not going to assume any other knowledge other than what I've developed so far in the class. Optimizing everybody understands. Minimize f of x. Suppose this is my objective, to minimize a function. Why is it useful to know f star? Is there a special value of y which is meaningful? Okay, so suppose I pick y equal to 0 and evaluate f star of 0. What do I get? It gives me essentially minimize f of x. So if I know f star of y for a particular function, I can just evaluate it at 0 and I'm done. So that's like the starting point why somebody even started to look at such a function. Once we have enough machinery, we'll try to say what he was trying to say. I'm not even going to use that word. But really, how the two are connected is via evaluation of this function f star at point 0. It's simply supremum of minus f of x. So if you can't do it directly, suppose computing such a function was easy, instead of actually doing the optimization, you could have simply evaluated the value at f star of 0, and you don't have to do anything else. It just you can say just rewriting of things, but that's not actually what is going on. Something more is happening here. Okay. So it does in fact become useful to actually do this. So this function is clear. So it's an important function. It keeps coming up in many different places. Okay. Now claim. F star of y. I'm going to write it again so that people don't have to go back. Supremum of transpose x minus f of x. X belongs to domain of f is convex irrespective of f of x being why is it? We don't have to do anything. What we did last class is sufficient. It's a supremum of what? In terms of y, it's just an affine function. It's just y times x minus some fixed quantity. So just by our previous arguments from the last class, this is in fact convex, irrespective of f of x being convex or not. That's the advantage of this function. See, we're doing these small steps one at a time. They'll all come together eventually. Okay, so let's try to compute some examples for which we can compute things. So which one do you think is the simplest function for which we can compute the conjugate? What is the simplest f of x? X. Very good. Okay. So suppose f of x is x. What is f star of y? So first pay attention to this function y transpose x minus x. You're supremizing this. So do I have to pay attention or I can just blah? What kind of function is y transpose x minus x?
It's a linear.
Yes, but due to very good boundedness, that's all.
Yeah, it's not bounded.
Yeah. So,
So that'll be infinity.
okay, so what bounds do I need to put?
No, in the sense I didn't get it.
So if I don't put any bounds, I do nothing. What is my f star of y? Okay, so then what's the next best thing I can do? If I didn't want this weird answer, is it at all possible to control it? Sorry,
Restricting the domain.
domain of what?
Domain of
Domain of f. Okay, suppose I restricted domain of f. What will happen?
And then maximum value.
At the largest point, depending on what y is. So that is also another way of looking at things. But what if it was x plus b, where b is non-zero? Sorry?
Okay. So we are getting the, for the first case, why we are getting the maximum is infinity, because we are looking at two lines passing through origin.
Okay.
Right now the intersection is shifted from the away from the origin.
Okay, so now this new function is how much? This.
Yes.
Now what happens? For what values of whatever this function is bounded? For what values of y this is bounded?
Still not bounded.
Sorry?
It's still not bounded.
Some values of y it is bounded.
It's negative directly.
What about y equal to 1?
And then it's fine.
What other value? Is there any other value for which it is bounded? You have to cancel this out. Either it goes to minus infinity or plus infinity. So for y equal to 1, this will be exactly minus b. So domain of f star y is exactly equal to minus b, where the domain of f star is the singleton point 1. What if f of x is x square? What is f star of y? Again, keep looking at the function y transpose x minus x square. Now you can easily handle this, right? Now there's no problem of running away to infinity. It's actually a concave function of x for a fixed y. So what is the optimizer? Something interesting will pop out, that's why I'm doing this. If you want to throw in a half somewhere to help you, you can throw in a half. If you want a half here, you can take a half. So what is the supremum of this? just brutally differentiate and put it there. Y minus x. So x equal to y. So evaluation is at x equal to y, half of y square. Somebody notice something? Sorry. No, I didn't write supremum here. This is just the function. After supremizing, you should get half at y square. Y equal, this is 0 at optimality. So somebody noticing, paying attention to what is going on? F of x was half x square. F star of y is?
Yeah, so conjugate is the same as.
So if I were to do it one more time, what would I get?
You again get half x.
So is this a happenstance or is something sitting inside which is giving me this? That if I do conjugate twice, I get back my function. What do you think is happening? And remember, you can compute conjugate for any non-convex function also. So that is a convex function. So you could simply plant x cube also as f of x. So this is an interesting property. And in fact, this will surely be in your homework, the third one. So let me just stick here that f star star is equal to f if f is convex and ap of f is closed. No surprise that this in fact turns out to be just simply the same. You take 2 times the conjugate, you get back your function. And the proof is actually not difficult. If you have been following what we've been doing so far, just take this, look at the epigraph, and use contradiction. That's the simplest way to prove this. That if it is not true, then something will happen. Separating hyperplane theorem will give you the answer. So this is the claim. That this is not an accident. For any f which is convex and whose epigraph is closed, this will actually be true. So you want to come up with an example where this is not true? So what happened here? If I take it one more time, what will happen? Sorry?
Taking the supremum of y transpose x minus plus b.
Flip the role of x and y so that you don't confuse yourself. So already you have f star of y, right? So take z. F star star of z is equal to supremum over the domain of f star z transpose y minus f of y.
Yes, the only one thing.
Yes.
So that is 1. So,
So
z minus
So z times
1 minus b. So
right
1 plus b. So minus
plus b.
So z times 1 plus. So that can go to.
No, what are you getting bulk?
Oh, I see.
See, there is nothing to supremize over. There's just one point.
Right, there's only one.
So you exactly get back here because this also satisfies the same conditions. So think of an example where this is not true. And that will only come if either is f is not convex or its epigraph is not closed, because the claim better be true.
Yeah, epigraph is defined as all the x comma t such that f of x is greater than or equal to b.
Yeah.
So then
It's always closed.
the closed, a non-closed epigraph where we have to somehow. If the domain is open, then the epigraph is open. Domain, you mean the x. Yeah.
So yeah, you need to think about they might appear very easy concept, but some thought is needed. So think about a function which is not convex. Is f star star equal to f? Let's do it for cube. Might as well. So let's suppose f of x is x cube. What is my f star of y? Right on this side just to make sure without the superposition. Okay. So you have to be careful because now this function is no longer concave. But let's try to do it. Y minus 3x square equal to 0. Hoping that this is in fact the optimizing point. So what is x? Optimal is square root y by 3. We're going to plant it there. Y times y by 3 is y times 3 by 2 by 3 minus y 3 by 2 by square root 3 here. And what is here? To the power 3, right? This 3 power
3 by 2.
3 by 2. So that is what you're going to get. So you do some ugly subtraction here and you get your answer. So it will be something like y to the power 3 by 2 by a. Take it one more time. What is going to happen? Made a mistake anywhere?
Yeah.
Okay. Is this the optimal point? Possibly not. So, correct.
But why it is saying that when you're doing a second part, right?
This itself is not verified at this point that this is supremizing. Because this function is no longer concave. So to be careful. Might be that it goes to minus infinity, possibly. So to be careful. So for this particular example, I have not worked it out already. So do check out whether it turns back to f double star x comes back to f of x or not. Appears unlikely. Most likely not. But I can't be certain. I have not worked it out. So what is the optimizing? X actually? Y transpose. It just goes up to infinity. So the domain itself is a problem. Okay, so we have to find this nicer function which is, at least gives us. Okay, so this example, scratch this example. We'll worry about it next time.
Yeah, the theory that you gave, it's not an FN only.
It's not f and only f. But if this is true, it better be. So that's why any convex and closed epigraphs will always give you. So that's why this is the nicest example to see. It's like the simplest, I would say. Linear is another. But the domain turns out to be slightly